Our next speaker is Lukasz Lamza, and he comes from the Pontifical University of Krakow in Poland, and he will talk about aspects of cosmic evolution relevant to biology.
I would like to express my thanks to the organizers and to the John Templeton Foundation and the Copernicus Center for Interdisciplinary Studies, who partially funded my participation in this conference. I will try to be brief, and if there are any questions during my presentation, please do not hesitate. I will be very glad to stop and answer any questions. What I'm about to present is a result of a study concerning the pattern of evolution of matter in the universe, which attempts to be at least partially quantitative. So although today I will focus on the qualitative aspect, there is this quantitative feeling I would like to invite you to understand a bit, although it will not be mentioned. I will try to refer to the observations more than to the interpretations. I believe we have a lot of theories, we have a lot of names and terms and concepts, but I think that the basic observations, uninterpreted observations, are most important. The background of all this project is my attempt to track the complexification of nature, starting from the exceedingly simple situation of the Big Bang, where we have essentially a homogeneous mixture of a couple of types of elements, to the present moment. And one thing that seems to be absolutely necessary if one is willing to do such a study is a list of all things. It would be pretty fun to have a list of all things. And as it turns out, there exists something like that, at least an attempt, which are library catalogs. So in my study, I use various kinds of library catalogs, which are lists, usually hierarchical lists, of all things that books are written about, which I think is a pretty good proxy for all things that we know of. And this is we cannot hope for more, yes? If there are any angelic beings out there who have access to more information, I'm willing to converse with them. But I think all that books are written of is a pretty good proxy for all we are hopeful to talk about. So this is a bit of the UDC, Universal Decimal Classification catalog, and I just love it. I think it's the best book ever written. It's better than a phone book. You know, everything is cataloged and has a number. I think it's a fascinating thing. Dumblons, one of my favorites. Dugongs, dull colors, as you can see, dummies and the dummy joints, dust, duplication, and so on. So this is the list of everything. Because I'm studying natural systems, I limit myself to the group 5. As I mentioned, this is hierarchical, so 5 is mathematics plus natural science, and 51 is mathematics. I'm not going to include mathematics, I'm just not. So 52 through 59, this is classes of natural science. This is on level 3, which means there are 3 digits. And I decided to go to level 5, which means there are 5 digits in the name, and there are 873 classes of phenomena. Some examples are given below: interstellar dust, friction, surface tension, radiolaria, blood, volcanism. It's a sort of a mishmash, a little bit of everything. There's absolutely no order. There's no hope of there being some sort of balanced hierarchy. I think it's a fun list to start with. And because my other purpose is demonstration and visualization, I chose to color these boxes by the class that they belong to. So each box represents one class of natural phenomena, and the colors suggest what basic group it belongs to. So yellows are chemistry, browns are earth, and all of the green is biology, obviously. Note that blues are physics. It's going to be important. So what is this? This is a phylogenetic tree of everything. Yeah, I like big words. And you probably recognize this bit. This is the phylogenetic tree of life. Origin of animals, radiation of animals. Oh, I'm sorry, the time scale has been cut off, but about here is 500 million years ago. About here is 1 billion years ago, and the time scale densifies so that we're going to 4.5 billion years ago is here. So the traditional phylogenetic tree of life has been upgraded to include also abiotic evolution back. So this is differentiation of Earth into atmosphere, hydrosphere, this is the lithosphere, and it goes back to the interstellar gas. This is stellar evolution, there's galactic evolution, and all of that converges in the Big Bang. The boxes have been, yeah?
So how did you build the tree?
Excuse me?
How did you build the tree?
Overnight. No, I'm just kidding. Overnight. My wife hates me for this. Just from different sources. Actually, when you think about it, this is all very non-controversial. It's the fact that the gas, the interstellar gas, turns into stars and planetary systems. This is actually, it looks pretty complex, but if you take a look at the scheme at the background, it's essentially very simple. It's just 4 or 5 basic facts.
I'm also quite curious about the question, like, what method did you use to construct this tree?
But do you mean the location of the boxes or the topology of the tree? Because this is quite a big difference. The topology of the tree, I think, is uncontroversial. There are disputes over where things branch in the tree of life naturally, the early history of Earth, but the basic topology, I think, is sort of understood. Big Bang, gas, galaxy, stars, planetary systems, planetary surface, abiotic chemistry, life, and then the location of the boxes is a tricky thing because each of them had to be put manually in place. So, but it's a long story. It's a first try. Don't ask me difficult questions about the location of particular boxes. Let's assume it's okay. So this is the thing. You will probably recognize certain phenomena like the Cambrian explosion thing, like the thing that the Earth's evolution had a Big Bang at the beginning. But what I wanted to talk about are these features, these 3 basic features that I think could be relevant to biology. So I'm mostly interested in the abiotic world because it's underrepresented in philosophy, I think. It's very fun to talk about human evolution and biological evolution and the Big Bang thing, the quantum mechanics, but philosophers hate things like stars and galaxies and planets. They're not as fun. For me, they're the best. So the first thing, so I'm going to talk about 3 features there. The first one is the punctuated nature of evolution, which means that the periods of the appearance of the greatest number of boxes are dense. They happen on very short time scales. The Big Bang is one of the good examples. Essentially 300,000 years after the Big Bang, most activity ceased. It was just a slow evolution, a little bit of chemistry. And 300,000 years is nothing in the scale of the universe. It's about 14 billion years old. On the scale of billions of years, most things happen. And the Big Bang, so the change from the first plasma, nuclei, atoms, basic chemistry, it all happens in the matter of thousands of years. Then there was the formation of first stars, which even now it takes about 20, 30 million years, whereas the gas around it evolves on the timescale of hundreds of millions of years. The end of stellar lives happens also instantly if we take a look at the things at the scale of their natural lives. The sun evolves for about 4, 5 billion years and will evolve for likely as long. But the final stages are exceedingly short. The bursts, the shedding of the stellar envelopes takes place in tens of thousands of years, which is just a blink of an eye from the perspective of a star. And this is where all it happens, the production of chemicals, minerals, the interactions between those, the stellar dust, all of this happens in the matter of thousands of years when compared to the hydrostatic stellar evolution that takes billions of years and no spectacular new inventions occur. So this is the punctuated evolution. This is what happens if we put all the boxes related to Earth evolution, including biology, on the time scale. Again, please note that this has been, there are two scales, effectively. So what is seen, I think, is the non-static pace, the tempo that's definitely non-static. There are bursts of invention, bursts of high creativity, and then periods of relatively little change. This topic has been brought up during this conference a number of times, and by now we all probably know how easily it is to dispute particular facts, the pace of the complexification of animals, for instance, but I just leave it as it is. Let's talk about controversies later. The second thing I wanted to mention is the micro-macro connection, which is seen fantastically in the early evolution of matter, where you have the large-scale evolution, the largest structures co-evolve with the smallest structures. The formation of nuclei inside stars. So nuclei are on the scale of 10 to the minus 12 meter, and the stars themselves are 20 orders of magnitude larger. And in between, there's very little structure. The changes in the pace of nucleosynthesis, the formation of new nuclei, changes the evolution of the star. So there's this bounce back effect. The changes on the smallest scales occur, and then changes on the largest scales occur, and then again and again. This is the magnification of the part of the early evolution of Earth. As we can see at the bottom, this is only 40 million years. So again, a blink of an eye on the scale of planetary evolution. But this is the first 40 million years of our planet, of our planetary system, in fact. About 4,567 million years ago, that's a nice number because it's easy to remember, 4, 5, 6, 7, is the first solid bodies dated in the solar system, 4, 5, 6, 7. And later it just goes very quickly. When we look at planetary systems in our galaxy using, for example, the Kepler satellite, usually about 20, 30 million years after the star ignites hydrogen, it's all over. The planets are on their orbits, they start a little shuffling, but the condensation is done. So it's just like that. And the micro-macro connection in this case can be seen if we put these are the same boxes, but they are now put on the length scale. 5 minutes? Yeah. This is the length scale, logarithmic. The smallest things, the largest things. And there's this progression from the largest things going down. Then there's the evolution in chemistry and physics, and it starts climbing again. So, for example, the planetary orbits, things like resonances, can only happen piggybacking on the earlier evolution of things on the size of meters and millimeters, which again is sort of, it's interesting to watch this. And the last thing is the global nature of change, which means that all of the colors are represented. There is no such thing as just a change in atmosphere, or just a change in biotic system in biosphere, or just a change in chemistry. And this is again the magnification of the atmospheric oxidation event about 2.3 billion years ago. And for reasons still unknown, this is very hypothetical. It coincided with a couple of things, both in chemistry, the first appearance of steroids, which are probably, there has to be oxygen for steroids to be synthesized in organisms, certain pigments. And then there are new geological formations related to glaciation. The oldest recorded glaciation is 2.4 billion years ago. So all of the glacial geology is represented first time in this period. So there's this quite interesting new types of rocks. These are this dark purple. Quite interesting compression of different types of things. It's not just one thing that evolves. We've got a little bit of everything. So the perspectives are natural. We can use boxes related to human evolution and human technology. Obviously, I didn't do that. I didn't know much about it. But again, it's a sort of fun list to take a look at, the UDC list of classes for human-related issues. Naval construction, naval bases just next to fruit growing and nuts. Interesting list in itself. And just one thing, because I don't do much human history, but one thing that always puzzled me is this extreme condensation of spiritual and philosophical creativity in the 6th century AD. I don't understand it. Maybe there's some research done on that, but it always puzzled me as one of those things that would have to be explained in some way. And this is suggestive of the compression effect that I mentioned. So I thank you very much for your attention, and thank you again for the opportunity.